Out there in the vast cosmic ocean drift some of the universe's most enigmatic objects, neutron stars. Born from the death throes of massive stars, these celestial bodies are tiny in size but colossal in power. Imagine a sphere, just a dozen miles across, cramming more mass than our sun. It's mind-boggling. They're stellar remnants, the leftover cores of stars that lived fast and died young. Their outer layers blasted away in spectacular supernova explosions, leaving behind these ultra-dense cores. Neutron stars challenge our understanding of physics, pushing the limits of matter as we know it. Think of the densest thing you can imagine. Now multiply that density by 1 billion, then 1 trillion. That's a neutron star. Join us on a journey to explore these cosmic wonders. Get ready to unravel the mysteries of neutron stars, the universe's most extreme objects. Neutron stars are like ghosts of stars past, faint echoes of giants that once illuminated the cosmos. They form when massive stars, at least 8 times heavier than our sun, exhaust their nuclear fuel. As the fuel runs out, the star's core, made mostly of iron, can no longer support itself against its own gravity. It collapses in on itself, a catastrophic implosion that triggers a supernova, one of the most powerful explosions in the universe. During this collapse, the core's protons and electrons are squeezed together with incredible force. They combine to form neutrons, subatomic particles with no electrical charge. These neutrons, packed together as tightly as the laws of physics allow, create an object of unimaginable density. A neutron star is essentially a giant atomic nucleus, held together by gravity. Picture a star, much more massive than our own sun, nearing the end of its life. It's a cosmic giant, its core a furnace where nuclear fusion has been raging for millions, even billions of years. But now the fuel is running out. The outward pressure from the nuclear reactions dwindles, no longer able to hold back the immense inward pull of gravity. The core, now mostly iron, begins to collapse in on itself. The collapse is so rapid, so violent, that it generates shock waves that rip through the star's outer layers, blasting them off into space in a spectacular supernova explosion. What's left behind is the star's incredibly dense core, compressed to an almost unimaginable degree. This remnant just a few miles across is a neutron star, the stellar equivalent of a phoenix rising from the ashes of a cosmic cataclysm. Only the most massive stars, those at least 8 times heavier than our sun, possess the gravitational heft to forge a neutron star. Imagine holding a teaspoon of neutron star material. The gravity of a neutron star is so intense that if you could somehow teleport a teaspoonful of its material to our planet, it would weigh billions of tons. That's heavier than Mount Everest. This mind-boggling density is a result of the neutron star's formation process. During the core collapse, protons and electrons are squeezed together with such force that they combine to form neutrons. These neutrons, packed together as tightly as physically possible, create an object of unprecedented density. To put this density into perspective, imagine cramming all the people on Earth into a single sugar cube. The intense gravity of a neutron star also warps space and time around it, a phenomenon known as gravitational lensing. Light passing near a neutron star is bent, creating distorted images of objects behind it. You might wonder, with all that mass crammed into such a small space, why doesn't a neutron star collapse in on itself? The answer lies in a principle called neutron degeneracy pressure. This pressure isn't caused by the neutrons pushing against each other, like gas molecules in a balloon. Instead, it arises from a quantum mechanical effect. The Pauli exclusion principle states that 2 neutrons cannot occupy the same quantum state simultaneously. In a neutron star, this principle acts like an outward force, resisting further collapse. It's a delicate balance, this cosmic standoff between gravity's relentless pull and the quantum world's pushback. But there's a limit to how much mass neutron degeneracy pressure can support. If a neutron star were to exceed a certain mass, known as the Tolman-Oppenheimer-Volkoff limit, even this extreme pressure wouldn't be enough to prevent it from collapsing further, potentially forming a black hole. Imagine a newborn neutron star, fresh from the fiery crucible of a supernova. It's incredibly hot, with a surface temperature of millions of degrees. But unlike our sun, which generates heat through nuclear fusion, a neutron star isn't powered by burning fuel. Instead, its heat is leftover energy from its violent birth, trapped within its incredibly dense core. Over time, this heat radiates away into space, and the neutron star gradually cools down. Think of it like a hot ember pulled from a fire. Astronomers have observed neutron stars of various ages, some young and hot, others old and cool. One such example, RxJ 1856 53754, is estimated to be over 1 million years old and has a surface temperature of around 400,000 degrees. This cooling process takes a very, very long time due to the neutron star's extreme density. Neutron stars are not only incredibly dense, they're also incredibly fast spinners. Imagine an object more massive than our Sun rotating on its axis, hundreds of times per second. This rapid rotation is a consequence of the conservation of angular momentum. Think of a figure skater pulling their arms in during a spin. Similarly, when a massive star collapses to form a neutron star, its rotation rate increases dramatically. The fastest known neutron star, PSR JADE 1748-2446 AD, spins at an astonishing rate of 716 times per second. This rapid rotation has profound effects on the neutron star's properties, particularly its magnetic field. As the star spins, its magnetic field lines get twisted and amplified, creating incredibly powerful magnetic fields, trillions of times stronger than Earth's magnetic field. Some neutron stars, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. These beams are generated by the interaction of the neutron star's magnetic field with charged particles surrounding it. As the pulsar rotates, its beams of radiation sweep past Earth at regular intervals, creating pulses of radiation that we can detect with radio telescopes. Imagine a lighthouse beam sweeping across your field of vision. Each time the beam crosses your eyes, you would see a flash of light. The discovery of pulsars in 1967 by Jocelyn Bell Burnell and Anthony Hewish was a major breakthrough in astronomy. Pulsars are incredibly precise timekeepers. Their pulses are so regular that they rival the accuracy of atomic clocks. We've talked about the incredible density and spin of neutron stars, but let's rewind to the moment of their creation. It all begins in the heart of a dying star, a core of iron larger than our Sun, crushed under its own immense gravity. This core, once the engine of nuclear fusion, can no longer withstand the inward pressure. It implodes in a fraction of a second, collapsing in on itself with unimaginable force. This is the engine of a supernova, a cosmic cataclysm that outshines entire galaxies. Imagine the energy released. It's like detonating trillions upon trillions of nuclear bombs simultaneously. The shockwaves from this implosion tear through the star, blasting its outer layers into space at tens of thousands of miles per second. Neutron stars don't just warp our understanding of density, they also warp space and time itself. Einstein's theory of general relativity tells us that massive objects create a dent in the fabric of space-time. So, a neutron star also warps the space-time around it, and this warping has some bizarre consequences. One of these is time dilation. Time actually runs slower the closer you get to a massive object. Another effect is gravitational lensing. Neutron stars with their extreme gravity act like cosmic lenses, distorting and magnifying the light from objects behind them. Deep inside a neutron star, the pressure is so intense that it might break down matter as we know it. Remember, atoms are mostly empty space. Electrons orbit a tiny nucleus made of protons and neutrons, but in a neutron star, even that structure is crushed. Some scientists believe that at the very core of a neutron star, the pressure might be so high that neutrons themselves break down. Neutrons, you see, are not fundamental particles. They're made up of even smaller particles called quarks. This quark soup, a state of matter called quark-gluon plasma, might exist in the hearts of neutron stars. If it exists in neutron stars, it could unlock secrets about the fundamental building blocks of our universe. So how do we study something we can't even see directly? Astronomers have become detectives, piecing together clues about the interior of neutron stars from the way they behave. One clue is their mass and radius. By observing neutron stars in binary systems where they orbit a companion star, astronomers can precisely measure their gravitational pull and estimate their mass. Combined with observations of their size, This gives us clues about their internal structure. Another clue comes from studying the way neutron stars cool down. The rate at which they lose heat depends on the properties of the matter inside. By observing neutron stars of different ages, astronomers can refine their models of the equation of state. Neutron stars don't always exist in isolation. Imagine two of these ultra-dense objects, locked in a gravitational tango, spinning around each other at incredible speeds. This, my friends, is a binary neutron star system, a celestial ballet with profound implications for our understanding of the universe. These systems are more than just a cosmic curiosity. They are, in a sense, astrophysical laboratories. As these neutron stars orbit each other, they emit gravitational waves, ripples in the fabric of spacetime, predicted by Einstein's theory of general relativity. These waves carry away energy, causing the stars to spiral closer and closer together. Think of it like this. Imagine two ice skaters, holding hands and spinning on the ice. As they pull their arms closer, they spin faster and faster. Similarly, as the neutron stars in a binary system lose energy through gravitational waves, they spiral inward, their orbital speed increasing to a dizzying pace. This cosmic dance culminates in a spectacular collision, a merger of unimaginable violence. The energy released in this event is greater than the energy output of our sun over its entire lifetime. It's a cosmic display of fireworks that send shockwaves across the universe, and we can detect those shockwaves right here on Earth. If you like this information about neutron stars, do like the video, comment, share, and subscribe to our channel for other similar interesting content. This motivates us to bring even more exciting content to you.